Normally when you learn logarithms, you're given a formula like, let's say, x to the y equals z, and then you're told that the logarithm is just log with a base x to the z, and that'll give you y, and you're just trying to find the exponent. And then you might be told to think of it like, let's say, how many times x multiplies itself in order to get z, and that'll give you your answer of y. And that works, and it's fine. I just thought it would be interesting to show you a different way of thinking about it, which is by, instead of thinking of how many times does x multiply itself in order to get z, seeing it as repeated divisions or counting divisions in like the next step after division. Let me show you like what I mean by next step after division. So if you subtract something like, let's say 8 minus 2, you just take 2 away, you get 6. If you wanted to divide it, you're just going to be counting subtractions. So 8 divided by 2 is asking how many times does 8 need to be, does 8 need 2 subtracted from it before it'll equal 0. So minus 2 once will give you 6, again 4, again 2, again 0, and you can count the amount of times you subtracted. 1, 2, 3, 4. So 8 divided by 2 equals 4. And now you can actually repeat divisions using logarithms. So instead of 8 coming first before 2, we're going to have the 2 come first. We're going to write logarithm 2, 8. And that all that's saying is how many times does 8 get divided by 2 before it equals 1? So 8 divided by 2 once is going to give you 4. Again is going to give you 2. And then again will give you 1. You count the number of divisions, 1, 2, 3, and you'll get 3. And that works. 2 to the power of 3 is going to equal 8. And I could end the video here. This was pretty much the different way of thinking about logarithms that I wanted to show you. But I thought it would be interesting to show how this could be applied to actually solving them by hand, even if it's in a bit of a tedious way. In order to do that, I'm going to need to show a couple cases. So the first case is if the base is larger than the number that's being taken. So like, let's say instead of log 2 of 8, it was log 8 of 2. Now, in order to solve this, we're gonna have to find a certain property of log, and I'll show you it. So x to the y equals z. That means that log x of z is going to be equal to y. And then if you were to write x equals z to the 1 over y, which is the same as that, you'd get log z of x equals 1 over y. So this shows that if you flip these two, the number on this side is going to get reciprocated. So now you can actually solve that. So instead of log 8 of 2, we're going to write log 2 of 8. And then whatever number that equals is going to be reciprocated. So we're just going to say it equals x, and it's reciprocated here. Log 2 of 8 is just 3. You could count divisions here and you'd be able to solve it, but we already know that it's 3, so I'm not going to do that. 3 equals 1 over x. You multiply that side by x, and then divide that side by 3, and you'll get x equals 1 divided by 3. On to the next case. What if the base is less than 1? What if instead of log 2 of 8, it was log like 1/2 of 8? How would you do it then? Because if you repeated divisions, is just gonna make the 8 go higher and higher instead of closer to 1. And you can actually still solve this with the repeated divisions way. You just have to change the log, like just how it's written. And I'll show you how you can do that. So x to the y equals z, which means that x to the negative y equals 1 over z. Because if these were to multiply together, then y minus y would equal 0. So that would mean x is to the power of 0, which would equal to 1. And if these were to multiply together, it would be z over z, which is also equal to 1. So that's why that works. And because 1 over z is just 1 over x multiplied by itself, z times, you can rewrite this as 1 over x to the power of y equals z. No. 1 over x to the power of y will give you 1 over z, I mean. Now, we're just gonna ignore this and just rewrite 1 over z as z so that this makes more sense for what I'm about to do. You can rewrite this as log 1 over x of z equals y, and then you can rewrite this as log x of z. That's going to give you negative y. You can move the negative, you can multiply both sides by -1, and you'll get log 1 over x of z equals y, negative log x of z also equals y. So these two are equivalent. So you can actually just reciprocate this and then add a negative, and you'll get the same answer. So if we were to rewrite that as negative log 2 of 8, well, you can actually solve this with repeated divisions. You're going to get 3. So the answer is negative 3. And that works. 1/2 to the negative 3 equals 8. Now on for the last step, which is, what do you do when it just doesn't divide evenly, even if you flip around the stuff like we've done for the past 2 cases? Like, let's say it was log 2 of 9. Well, what you can do here is you can actually just start dividing by, you could just start doing the repeated divisions again. So 9 divided by 2 is 4.5, divided by 2 is 2.25, divided by 2 is just going to be some number that's less than 2, and then you stop there because it isn't able to keep being divided by 2 and giving you a whole number. So that'll give you 3 divisions, 1, 2, 3. So you'll get 2 to the power of 3. 2 to the power of 3 is going to be the closest number to 9 that is a power of 2 that is still lower than it. Now, I'll show you what we could do about this in a second. First, I have to show you the property of... First, we got to remember the property of logarithms, where if you were to add log x of z and log x of w, you get log x of zw. Knowing this, we can actually take 8 out of that, move it over, and then we could just keep solving. Let me show you. So we could rewrite this as log 2, 8 times 1 over 8, because we don't want it to actually affect the number inside there. It's going to equal the same thing, times 9. And we're using 8 because it's 2 to the power of 3, which is how many divisions we got. Then we can, using that property I showed you before, we can take this 8 out, which is going to be log 2 of 8, so that's 3, plus log 2 of 9 divided by 8. Now, I could end the video here. You could stop watching. I'm just going to keep going for a bit just to demonstrate that you could just keep doing this over and over again to approximate it better. So we got 3 log 2 9 over 8. 2 isn't going to divide into 9 over 8 because it's bigger, so we're going to have to flip it. So we're going to get, we're just not even going to write a 3. So that's equal to 1 over log 9 over 8 of 2. Then we can just solve that. That's going to go in once. You're just going to have to take my word for it. I'm not going to explain why with the divisions, but you could just check for yourself if you want to. So that is just going to be 1, because 9 over 8 only goes into 2 once before it becomes less than 9 over 8, plus log 9 over 8, and then we're going to divide 2 by 9 over 8, so that's going to be 16 over 9. And then we're just going to repeat it again. 9 over 8 is going to go into 16 over 9 once, so we're going to make this a 2, plus log 9 over 8, and I don't know, 8 times 16 off the top of my head. Let me use a calculator. So that's going to give us 128 over 9 times 9, which is just 81. And you could just do this again and again and again. Then once you get a number where it won't go in even just once, you can reciprocate it and get another fraction, have like a bunch of nested fractions that just go on for infinity as close as you want to approximate it. But yeah, that's pretty much it. Thanks for watching.